We will start again. Richard will continue with the interesting talk he started today about the survival of Ernst Ising and the struggle to solve his model. The last slide of yesterday was a Solvay Congress in the 30s, no? So you can continue with your interesting exposition. Thank you.
Okay, this is the second and last part of the life of Ernst Ising and the Ising model, the solution of the magnetization which exists in higher dimensions. So my last transparency or the talk yesterday is here summarized in some way. I show you the small group of people working in Hamburg University. It was a Professor Lenz. He had a small group with people who made their thesis, and one of them was Ernst. And I included here a lady, Lucy Mensing. She was the third student who made the thesis by Lenz, and she worked closely with Pauli on the new quantum mechanics. So here we have two people who worked on the microscopic level of the problem of ferromagnetism, the quantum mechanical problem. Here we have Ernst, who worked on the statistical problem. And here we see Otto Stern, who made experiments, you know, the Stern-Gerlach experiment and other further experiment with molecular beams. And in fact, the Stern-Gerlach experiment was the first experiment to show the spin degree of freedom, which Pauli found when Ernst had finished his thesis. So Pauli was invited in Brussels, and there he could present the model of Ernst Ising in the form we know it now from our lectures.
But excuse me, please.
Excuse
me, please. I have a question. If other participants can see your screen, your presentation. I don't see the presentation. Is it only my problem?
I can see.
I can see. Sorry, that's my connection. Excuse me.
Okay, sorry. So I think it's now a good point, the right place to discuss about the naming of the model. Ising suggested Brash in his diffidence and esteem in science to include Lenz in naming the model. So Brash, who published the first review and history about the Ising model, he was the first to call the model Lenz-Ising model. So, however, later it was overlooked that Brash considered this as a failure. In his second volume of the book, The Kind of Motion We Call Heat, on page 12, he wrote, "It is usually futile for historians of science to try to change established nomenclature." And he added the footnote 21, "My attempt to add the name of Wilhelm Lenz to the Ising model in statistical mechanics has been a failure." However, others kept the naming of the model by Lenz-Ising model in later publications, although the relevant citations of the scientists who worked on the Ising model, they always cited this model as Ising model. Now I go through how this Ising model was recepted by the other scientists. The first citation after 1913 was by Van Vleck in 1932. He was called the father of modern magnetism, and he published the theory of electric and magnetic susceptibilities. And you see from the citations and the comments to the Ising model that the model indeed was not completely understood. For instance, he cited, in seeming contradiction, Ising found that classically there was no ferromagnetism regardless of the crystalline arrangement. This, however, was because Ising arbitrarily took the coupling between elementary magnets to be proportional to sigma Z1 and sigma Z2, nowadays we call it mu, rather than to the complete vector product. I mean, that was also the argument to which Pauli responded in Brussels, and Van Vleck was in Brussels, so he did not really understood what Pauli meant with his comment. And even in absence of magnetic field, there should be a discontinuity in specific heat as one passes through the Curie point. I mean, that's the result first noted twice. And in terms of Heisenberg, this is because and so on. So it was the belief that there could be only a jump in the specific heat when the phase changed. However, it was clearly made clear by Van Vleck in this book that Bohr and Henrietta van Leeuwen had already shown that ferromagnetism is a quantum phenomenon. The new quantum mechanics is perhaps most noted for its triumphs in the field of spectroscopy, the macroscopic aspect, but it is less heralded success in the theory of electric and magnetic susceptibilities. So ferromagnetism and ferroelectricity must be regarded as one of its great achievements. So it was recognized that the model, in fact, I would say it was important. But now the time changed. Hitler came to power by the Enabling Act. New anti-Semitic laws followed, which forced all Jewish scientists, but not only them, to resign their position and or leave Germany. However, Pauli in 1928 was appointed professor of theoretical physics in Zurich in Switzerland, and he already left Germany. The German annexion of Austria in 1938 made him a German citizen. He was an Austrian, which became a problem for him in 1939 after the outbreak of World War II. So he left Europe in 1914. He tried in vain to obtain Swiss citizenship, but he couldn't reach. So therefore, he moved to the United States, where he was employed as a professor of theoretical physics at the Institute of Advanced Studies. And only after the war, where he had already become a naturalized citizen of the United States, he returned to Zurich. And also Otto Stern had to resign his post at the University of Hamburg, and he emigrated to Pittsburgh, becoming a professor of physics at the Carnegie Institute of Technology. What happened to Ising? Also, Ising was concerned by the law of restoration of the professional civil service. In German, Gesetz zur Wiederherstellung des Berufsbeamtentums. So he was dismissed from teaching at a public school. But he could later found a position as teacher and headmaster at a boarding school, you see him here, for Jewish children near Potsdam. The buildings there had been a summer recreational home, but then one was turned into a school when Jewish children were dismissed from public schools and educated at these Jewish schools. Johanna, his wife, could stay at the College of Commerce, not a state institution in Berlin, for a longer time, where she privately worked with Professor Franz Eulenburg, who was dismissed as a Jew not until 1935 because he had to supervise so many doctoral candidates. So he only was dismissed only later. In 1943, he died in the prison of Gestapo. Hamburg University was also forced to vow of allegiance of the professors of the German universities and high schools to Adolf Hitler and National Socialistic states. So Heidegger, who was also vowed for that, but he recognized the much celebrated academic freedom is being banished from the German universities. So this was a bad development in Germany, and nevertheless, science went on. And Lothar Nordheim, for instance, also cited 1934 Ising's publication. That's one of the rare publications Ising himself got to know. It was a contribution on the quantum theory in the Müller-Poyer's textbook on physics, a very important review edition for several topics in physics. And he starts his short review with a critique of the classical theory. He notes that there is no explanation of the strength of the inner field by classical interaction. And he said dipolar magnetic interaction is too weak. Indeed, it is an exchange interaction. And that the theory contains inner inconsistencies. And he names the thesis of Henrietta Johanna van Leeuwen. He then concludes that magnetic properties of matter are pure quantum mechanical effects. But one always looked for some better models than the Ising model, which was too simple. But he recognized, incidentally, it was Bloch's calculation after Heisenberg, is in agreement with the results of the classical theory that in a linear chain, if only the dipole interaction of the individual magnetons is taken into account, no ferromagnetism is possible. So he recognized that Ising has shown that mean field theory is not correct in one dimension. Now this was the reason why Bethe, 1935, improved mean field theory. He thought, well, I have to improve mean field theory in order that in mean field theory there is no phase transition in one dimension. That was an important step. And he did it in the way that he considered not only the position of one spin, but also of the neighbors of the spins in his models. So in a change, this would be the two neighboring spins. And he took their position, parallel or antiparallel, into account in this paper, and he came to a phase transition temperature modified from the mean field theory, where in the denominator you have the number of the neighbors Z. And for Z, for a change, would be 2. And this would be infinite, and there would be the phase transition theory, phase transition temperature, the Curie temperature would be 0. The next step in developing the Ising model was Peierl's paper, a very important paper because he could show that in 2 dimensions one should expect a phase transition, a finite Curie temperature for that. And how did he consider this? Well, he looked at the number of plus and minus spins up and down, or into the direction of the field or against it. And then he looked at the expectation value of this number of one sort of the spins. Let's take the minus spins. And he plotted the 2-dimensional lattice and looked at the islands of plus spins in the islands of the minus spin. He made a slight error because he didn't look of islands in islands. This was later corrected, but it didn't change his result. So by considering the energy of the boundary of the islands, he could show that in 2 dimensions there is a phase transition. But he couldn't find the phase transition temperature. Well, in 2014, Claudio Bonatti made a paper who asked, could we extrapolate Peierls' argument, so this inequality, he looked for one sort of the spins, to higher dimensions. And he did it. It's a mathematical paper, and I show you the result. Here you have the curve of temperature. It's the inverse temperature, in fact. When you increase the dimension, it's up to 100, fantastically. That's a purely mathematic thing, but it shows that if you go with the dimension to lower and lower and lower dimension, you come to an infinity at 1 dimension. But at 2 dimension, you have a finite value of that. So it became clear that the Ising model has a phase transition. 1937, the next textbook appeared. It was by Francis Pitta. It was an introduction to ferromagnetism. And this is the most prominent publication which cites Ising's thesis. He gives the calculation of Ising as I presented you yesterday in his book. So it follows the publication, but in my opinion, he also had information on the thesis. Pitta recalled that during his time in Berlin, he was an American, but 1925 to 26, he was with a stipendium in Berlin. He heard Max Planck speaking about thermodynamics. He attended the colloquium of Erwin Schrödinger introducing wave mechanics, and he taught himself electricity and magnetism from the textbook of Max Abraham. Now, later, it is a textbook Abraham. Well, I forgot the name. It's a textbook which we now use also in our lectures. And he received 1928 his degree from the Columbia University. And therefore, because of his detailed calculation he gives, I think he had access to Ising's thesis, maybe by some contact between Berlin and Hamburg or something like that. And he, in addition, Ising just was interested in the magnetization, and he is interested also in the complete thermodynamic system, so he gave the calculation of the specific heat. And you know, in 1 dimension, the specific heat of the Ising model has a peak and then goes down to 0. And nowadays, this peak is known in literature as Schottky anomaly, because the Schottky paper I mentioned yesterday, he considered a 2-state system, so to say a spin dot in some sense, a 0-dimensional system, And he looked at the thermodynamics of the system, and he calculated, for instance, also the specific heat, and it just looks like similar than this specific heat for the one-dimensional Ising model, and since that time is called Schottky anomaly. This, for instance, is an example of a paper which is not cited, but it is cited that this and this is a Schottky anomaly without reference to the paper. Therefore, it's difficult to find it then by just going through the web of science. Now, in 1937, there was a famous congress in Amsterdam. It was the Van der Waals centenary. And from the question discussed at this conference, you see that it was very difficult to understand the phase transition for the scientists. So there were questions which I find very interesting. How can the gas molecule know when they have to coagulate to form a liquid or a solid? And the question was, is it enough to have for a system, if you have the Hamiltonian, one partition function? The audience did not agree on this question, and Kramers let vote them, and it was 50 to 50, almost 50 to 50, that you need for each phase a partition function. And it was not known how for a finite system one could explain a sharp phase transition. Now, Kramers suggested that you have to use the thermodynamic limit. The system size goes to infinity, and then the partition function could develop a singularity, and then the phase transition would set in. Even at that time, Kramers already had found the transfer matrix method, and he mentioned it at the conference, but didn't give any details. Time changed again 1 year later. On 10th of November, 1938, the pogrom in Germany took place in Kapput and other towns. So the school where Ernst Ising was teaching was destroyed, and the Jewish, anyone who could save themselves at such a late hour left Germany. And the destruction of this school and there is a memory on that by the so-called Stolperstein for Gertrude Freitag, who was the leading person in this school. It was a teaching experience for young people, new ways of teaching them and so on. And 2018, there was in Kapput an exhibition on this event. Well, Ernst Ising tried to rescue the pupils, and he came to conclusion after an arrest by the Gestapo that he and Johanna had to decide to emigrate to the States, and they decided on after 27 January of 1939 to emigrate to the United States. But in order to emigrate, he had to wait 2 years, or about 2 years. And in order to survive in that time, he thought he had to go to Luxembourg. So on 1st May of 1939, he arrived in Luxembourg at the small town Mersch, where he and Johanna got one of the room in the hotel you see here. I have some sound in my talk. Do you hear me?
Yes.
Yes, okay, I proceed.
Yes.
So they were safe in this hotel, but it was very difficult for them. They thought they could wait there 2 years. That would be in 1941. And in 1941, the 2 years waiting period would be over. The money for the trip from the Spanish border and the boat passage was available. Almost all papers were ready. Only one more specification in 1941 was required of where our sponsors would lodge, Johanna wrote in her recommendation. They needed this, but just one day before they got this recommendation, the American consulate were closed and they were captured in Luxembourg in 1941. Now, in 1939, already the World War II began. And it was also on 9th of September that Tom Ising was born, and so the family consisted now of 3 people. Now, during the war, they were safe until 10th of May, 1940. A second event, not only the opening of the Hamburg University, but the occupation of Luxembourg, happened on Ernst Ising's birthday. They had to remove from the hotel to a 2-room flat in Berschbach, Mersch. No more money from abroad, but they could get money from Germany because now Luxembourg was a part of Germany, and Ernst could teach at the Jewish school until October 1941. But then also this teaching was over and he worked as a shepherd. But in the time 1939, just nearby Luxembourg, Mersch, in Strasbourg, there was the first magnetic conference in May. It was the first international magnetic conference. Attendance of the meeting was just by invitation. Reports were circulated in advance, and the gathering was focused around 6 discussion sessions lasting 3 hours each. Now there was several people, 2 people I can identify. It was Becker and some were here, Gerlach. They were invited from Germany. Kramers was there, and also the British scientist Bates. He gave a report on this meeting. Also, I will come to this a little bit later. And of course, Weiss, the old scientist, was the prominent man at this conference. But the climate of the conference was strange. The rector of the university then closed the conference in a final toast to the honor and preservation of free scientific thought, as it had just been exemplified at the conference itself. It was a noble thought, grotesquely at odds with the world collapsing around him. A citation by McRae in the year 2014. And there are also other recommendations about discussions if Strasbourg is a German city or a French city. Now, Becker was a German physicist who also wrote in 1993 a prominent, even nowadays cited book on ferromagnetism. He, together with Döring, the Becker-Döring, is well known in Germany and Austria. And also he cites the Ising model. And the interesting is, and this is important for our talks tomorrow that he considered the phase transition by the word Schwarmbildung, so the flocking behavior of the elementary spins. Bates commended after the war 1946 in Nature the book, and he said it is very unfortunate that this important work should have appeared at such an inopportune moment in the world's history, when it will be difficult for most of the English-speaking peoples to obtain a copy of it. Those of us who had the pleasure of meeting Professor Richard Becker at the 1939 conference on magnetism in Bristol and in Strasbourg must sympathize with him, and in no small measure. So the book is a standard textbook, and he presented the closed chain because it could be easily calculated, and he presented this inverse susceptibility of the Ising model in order to demonstrate the difference, it's an exact result, into the difference of the approximation of the Curie-Weiss theory. So it was known that Curie-Weiss theory is an approximation. It didn't really work in one dimension, and they already knew that in 2 dimensions the Ising model had a phase transition. Now I can give you a short chronology of what we know so far. So from the foundation of the Hamburg University, Ising thesis, Pauli's 4th quantum number, Heisenberg's exchange interaction, and Pauli's citation of the Ising model. Over several citations, we came to Peierl's phase transition in D = 2. But the solution of the Ising model was waiting more. But time already changed in a bad manner. In May of 1940, the Germans occupied Luxembourg and declared it part of the Greater German Reich. This is a report Ernst Ising gave in the year 1967 to the Peoria Journal Star Sunday, December newspaper. They even allowed the Jews to fight in the German army, and you can imagine how happy they were about that. There were many people shot every night. When the Nazi came, they took Jewish children out of the schools, and Jewish people were deported. But Mrs. Ising is not Jewish, and they left us alone. That were the law in Germany and also in Luxembourg. We weren't allowed to give to the collection of the Nazis. In other countries, Jewish partners in marriage were taken to concentration camps, but not in Luxembourg. We had a patch of land where we grew vegetables to work for farmers. I helped at the monastery you see here. Behind the monastery, there was the railway track. And at the monastery, old Jewish people were living and collected from Luxembourg and then put to the railway, to the train, waiting on the railway, on the track to go to Germany, to concentration camps. And in 1942, there was this Wannsee conference, and there is one copy survived from this conference, and I do not want to go to the details. But on October 6, 1941, all Jewish families in Luxembourgville were deported to concentration camps. But because of Johanna was a German, an Aryan woman, they were safe, all 3, Ernst, Tom, and Johanna. and he worked to help the old people as long as he could do. But then he even had to work on the railroad for the Nazi. It was the Maginot Line. They had to remove all the rails that ran into the Maginot Line just north of Thionville in France. He had to go there, and those railroad was then taken to Russia because they needed at the Russian war for Russian railroads in the war in the East. So it was a very bad situation for the Ising, and it was very dangerous. But physics made its success. In 1941, a dramatic change, not only in the life of Isings, but in the struggle to solve Ising's model was made. A breakthrough was made by several scientists. I show them immediately, but the most important breakthrough was made by Wannier, who was in Leiden in the Netherlands, also in danger, and Wannier in Texas. He could manage the publication in the Physical Review. And from the abstract, I can cite a sequence of finite matrices is found whose largest eigenvalue approaches the partition function of the two-dimensional square net as the matrix order gets larger. It is shown that these matrices possess a symmetry property which permits location of the Curie temperature, and it's given. The symmetry relation also excludes, and that's also important, certain forms of singularities at TC, e.g. a jump in the specific heat. It couldn't be mean field theory. However, the information thus gathered by rigorous analytic methods remain incomplete. So let me demonstrate what these transfer matrices are. So I show you the linear chain. And here you see the partition function of the linear chain. You have to sum up over all configurations of the spins. And here you have the Hamiltonian of Pauli for the Ising model, For the Ising model, you have the interaction of the spin, the exchange interaction, you have the magnetic field there. And if you look at this expression, you have the exponentials. You can write this expression as a product of matrices, only containing two spins. And if you look at these matrices for the two spins and all its configurations, these two-dimensional matrices have these simple elements. And if you take the trace of the product of these elements, you get the trace of the product, and the product, because when you diagonalize the matrix, you have the sum of the two eigenvalues of this matrix. And the eigenvalues of this matrix are given by this expression you already know from the thesis of Ernst Ising. So it is a very simplification, you see. But it's based on something which was completely unknown when Ising started with his thesis. And moreover, they also found a symmetry property called duality in D = 2. It's a relation between the low temperature expansion of the model and the high temperature expansion. And if you bring these two together, you get an equation for the phase transition temperature. So the problem Peierls couldn't solve, they could solve here with the duality property of the transfer matrix. Now, in the summer of the year 1933, Lars Onsager, we already have seen, he started his, about the same time, his studies of chemistry and physics and mathematics in Norway. He was in Europe. I had a question yesterday about his topic. He treated at that time, and he worked on electrolytes, and his paper were very important. And he, in his visits to Europe, he went to visit important German, Swiss, and other scientists. And so at that time, in 1933, he visited Falkenhagen. In literature, it is said he is an Austrian electrochemist, but it is a German electrochemist who was also in Rostock at the time, and Schottky had contact to him. But at that time, I do not know where he met him in special, but it could also be at Debye in Zurich. Anyway, he visited Falkenhagen to discuss with him about electrolytes. And he had his discussion, but in the evening, Falkenhagen was unwell at the time, and he asked his sister-in-law, Gretel or Margarete Arletta, to entertain Lars. Gretel saw him coming up the stairs, a very handsome young man who her brother-in-law had told he was well ahead of his time. They went out to dinner, but Lars was his unusual reticent self. After dinner, he fell asleep on the patio and then woke up and asked, "Are you romantically attached?" They became engaged 8 days later. Margaret was 28 and Lars was 29, and they got married on 7th of September 1933. He had to go back to the United States, and he got a position at Yale at that time in 1933. And now, at that time, in 1942, the United States joined the anti-Hitler coalition. And American universities during the war were less busy than usual. Many students were off fighting, and scientists were doing military research. But since he was married to Gretel, which was an Austrian, she was an alien with an Austrian, he and she was an alien, and he was not part of this military research. And consequently, he had time to prepare the next jewel in his crown, as it is cited. It is the solution of the two-dimensional Ising model. He became acquainted with the two-dimensional Ising model with a student from him. It was Elliot Montroll, who had worked, and I see, I go back one transparency. Yes, I forgot to mention all the other people, beside Kramers and Vanya, who came to the transfer matrix and to the simplification. It was Montroll, it was Lassettre-Howe, two persons, I have only one picture from them. So many other scientists, these two for instance, they already became to know with the transfer matrix, and Montroll explained Lars that they had this new method to attack the Ising problem. Now, Onsager had a lot of time, and he tried to solve the two-dimensional Ising model. But the transfer matrix for the two-dimensional Ising model is a much larger matrix than this 2x2 matrix of the linear chain. Indeed, it is an infinite matrix you have to solve for the eigenvalue of this awful matrix. And he couldn't do this without mathematical knowledge. So he had to learn about matrices, about algebraic problems, about eigenvalue problems. And he had to search for symmetry properties of the transfer matrix in order to reduce the problem, because finally he had to find the eigenvalues of this matrix in order to get the partition function. And therefore he looked at product algebras and so on, and he started with a 3 by 3, 4 by 4, 5 by 5, 6 by 6 problem in order to find out the symmetries, and he proceeded. The history is in this paper by Longway Higgins and Fisher described. So he proceeded by enormous work to solve the two-dimensional Ising model. So he could only solve it in magnetic field 0, no external field, but he could calculate the specific heat. So we already knew the specific heat shows in one dimension, no phase transition, a Schottky anomaly. In two dimension, he found, and you see here the two-dimensional result, he finds a divergence, a logarithmic divergence. I add here results done later by numerical calculations. The three-dimensional Ising model, it has a power law divergence. We have heard in the talk of Bertrand that we have scaling laws, we have power laws, we have divergences, and this is one example of a divergence of the specific heat for the Ising model, or because of universality for the fluid, for the mixture, and for alloys. And here you see, for comparison, the mean field theory. So it was a very astonishing result, and it needed many years to understand this. Van der Waerden already in 1941, and also in a discussion with Petter, he said the theoretical reason for this new phase is that below this temperature there is a long-range order, and this order is with considerable probability preserved over any long distances. So you have a diverging correlation length. We have heard all these things yesterday. Now, how did the life of the Isings proceed? Well, they lived in Mersch. I show you here how the building where they lived looks today. It is a house in Schwartenrue, Jean Magerue, Mozartstraße was it called in German, and they lived there from 1942 until 1946. They waited there. I already told you that Ernst had to do unfree labor. He was insured. He could stay at home, and they waited and waited, and they heard radio. They have heard that on 6th of June 1944, the D-Day, that the American soldiers and the armies of the other countries were invading France, and on 1st of September, they almost reached Luxembourg. There no railway service were, the Germans flee, and on 10th of September 1944, they were freed by the Allies' army. So they were safe. All three were safe. And then they had to wait again 3 years, and on April 1947, they left Rotterdam on board of the freighter Lipscomb Likes and arrived on 21st of April 1947 in New York. Now, the story of the Ising models was not finished, but the life of Ising started in the United States just from the beginning. And in 1951, he could make contact by letter from Pauli to Ising, where Pauli told him, "I'm very glad to know that you survived the Hitlerism alive and that you have a job." He came to New York, he looked for a job, and he found again a position as a teacher, first at the college. Dr. Ising taught physics and mathematics at the State Teachers College in Minot, North Dakota, and then from Minot he came to Bradley University in Peoria, Illinois, where he taught physics at the university. You see him here in the late 1975, and he retired 1 year later. So finally, he also could be a teacher, even a university teacher. He loved physics. But the Ising model, his problem wasn't solved, because Onsager only could calculate the partition function in external field 0. And in 1948, at some conferences, and some conference in Cornell, and also 1 year later in Florence, he wrote on the table the result of his calculation of the magnetization. And that was really an important result. It was a power law with a rational coefficient. The magnetization goes to 0 if you increase the temperature with a power law Tc minus T with an exponent of 1/8. He couldn't publish this result because he had problems with the mathematics. He didn't want to publish the result without showing that it was exact. And the knowledge in order to calculate the magnetization was very, very complicated. So Onsager's solution, he worked together with Kaufmann in 1949 and with Montreux in 1943. So they had to simplify Onsager's solution in order to proceed to really derive this result state by state. And 1949, Kaufmann and Onsager could calculate the correlation function. And this was the important step, because you have the correlation function in field 0. And from the correlation function, if you look at the correlation in infinite distance, you can come to the magnetization. And this 1952, Young attacked the spontaneous magnetization of the two-dimensional Ising model is calculated exactly. The result also gives the long-range order Van Werden already said in the lattice. So it was, Young described his work. He said, starting in early 1951, I worked on the Ising model intensively. He wanted to calculate the spontaneous magnetization. I was led to a long calculation, the longest in my career, full of local tactical tricks. The calculation proceeded by twists and turns. There were many obstructions. I almost gave up. Finally, all the pieces suddenly fitted together, producing miraculous cancellations. And I was staring at the amazingly simple result. So he could reproduce by these methods, and by all the knowledge in between was made, Onsaga's result. But was everything done? Was it solved? Well, it was a quite different way to come to the magnetization of the Ising model. Well, we have here the timeline starting from Pauli's presentation of the Ising models through the textbooks, the citations of Ising's, through Onsaga's exact solution, through Kaufmann's and Onsaga's correlation functions, finally to the magnetization. But only 20 years later, in a paper on the Onsaga-Young value of the spontaneous magnetization, it was shown that the value of the spontaneous magnetization for the two-dimensional Ising model computed by Onsaga is indeed the appropriate derivative of the free energy with respect to the magnetic field. The argument is based on a simple application of the duality transformation. Now it really was shown that Ising's task was finished. It was calculated for the two-dimensional model in this way, and the authors are these four people: Galavotti, Jona Lasinio, well-known Stella, and Benetin. So two were students at the time, and then their professors, Galavotti and Jona Lasinio. So the first review was made by Brush, I already have cited, and the comment to the fate of Ising's life is made by, and his problem, by Michael Fisher in this publication. Ernst Ewing solved the model explicitly for d = 1 in 1924, too soon. However, he became a refugee from Hitler's Germany. Much later, he worked for almost 3 decades as a professor of physics in Bradley, Peoria, Illinois. But to solve the Ising model for d = 1 proved intractable for many years. Furthermore, as we now know well, the available approximate solutions were quite misleading, and problems remained. Why you get rational exponents? And this was then the scientific problem for the late works after Ising came to the States. After the 60 years, it was the work where you found renormalization group theory, all the scaling laws you have heard yesterday, and it's also described in a very large paper by Niss. It was his thesis about phenomena models and understanding, the Lenz-Ising model and critical phenomena. And there are many reviews, especially also Sigismund Kobe had written several papers. One of the last is in the Brazilian Journal of Physics. And also somebody of Peoria, Mrs. Robinson, had a manuscript in the year 1995, which also contains many information on the life of the Isings. Now let us speak at last Ernst Ising. He said in an interview, his most memorable moments, Ising said, have been spent with other physicists. He explained as when he was a doctoral candidate at the University of Hamburg. Classical physics was under severe attack at that time. Well, we need a new microscopic theory. Several attacks and lectures given by people such as Niels Bohr and Max Planck helped to revolutionize physics, and of course Heisenberg, Pauli, and all his colleagues, and this to its present state. So he memorized the Hamburg time as a very good time for physics and a good time for himself. So let me finish with this, and I thank Tom Ising, Sigismund Kobe, Karin Reich, Kurt Scharnberg, Bertrand Bersch, Ralph Kenner, Yuri Holovach, with whom this work was made, and I thank you for your attention. Thank you very much.
Okay, thank you very much. Okay, very interesting talk. We have time for the questions. I have a question.
Yeah.
What do you think about the solution in 3 dimensions? Is it possible or is realistic to have an analytical solution, or maybe we need the solution in 2 dimensions is constrained by the conformal group? It is possible to find the analytical solution because you have a large group of symmetries. What is your opinion in 3 dimensions?
Yeah, well, I'm not a specialist on that, but I asked myself this question, and my first answer would be never give up. You do not know. I do not know any proof that there is no solution. I got to know by Bertrand that, for instance, you could solve the 2-dimensional Ising model, the magnetization, at TC by using conformal group. So there's a special point where you could use conformal group, and also you use this to explain why you have a rational exponent for the magnetization and the other quantities. There is also there are papers which show that this is the problem for computer calculations is very complicated, is an NP problem, and therefore a non-polynomial problem, and therefore you can attack this. Binder said it's the workhorse for people working on computer simulations, but I do not know if you can find really what you can consider as an exact solution. I mean, there are also some things, they use experimental mathematics, but they didn't proceed even to the result of they could find the 2-dimensional solution by experimental mathematics, but you do not understand why this happens, because the computer finds the solution. And so I do not know, and I say I would not give up, but you need new ideas. You need hidden symmetries. Maybe you find a hidden symmetry. And that's also a point. I mean, what yesterday Bertrand told about Landau theory, it was Landau presented his theory in 1936. And this was an important step because he formulated mean field theory, so to say, with an order parameter in its symmetry. Mm-hmm. And symmetry matters. That was also for both Young and Onsager. They had to find the hidden symmetries in order to simplify. So that's...
Thank you. Another question? Comment?
I would have one.
Yes, please, Wolfgang.
Yeah. Reinhard, do you have any new information? I mean, the magnetic susceptibility that is not solved exactly. Is there anything new on that?
No. Well, I have to say no. In the last years I didn't follow the results. So I mean, there are the interest in the Ising model and the solution, because I said didn't give up. It is not dead. Always people try to do it. I mean, we had a period where somebody believed that he had an exact solution for the 3-dimensional model, and maybe some people believe it even now. And but you should look for these symmetries to solve. And even if you do not solve it, you find something, and that's to the talk Ralph gave this afternoon. If you look to solve the 3-dimensional Ising model, you find things which you can use somewhere else, very important things.
More questions, comments?
May I add one? I mean, maybe you remember there's a paper by Fisher, but I forget where it was and when it was, where he proved, or he claims that he has a proof, that there cannot be an exact solution in terms of the known mathematical functions.
No, I do not. If I would have cited this if I know it.
But I don't recall where it was. And
do you know any time when this would be? Because Fisher followed the Ising model. Well, it's an important person since the 60s. And I followed some conferences where all these theories about phase transitions were developed, and how it was important to have the Ising model to go to find all the other methods.
It was, I don't recall exactly, but I would think it's around 2000 or so. It was a relatively new one.
Well, I will look at this. If I find something, I always find things on the net by chance, and I don't give up, and I try.
I was also looking for it, but I could not easily find it again. So it's,
but
one has to check precisely what the statement was. I think it was in terms of the known mathematical functions. There cannot be a solution.
Because I mentioned this paper from 2014 about this Peierls transition temperature, so to say. It's not the transition temperature, but the temperature where you have an island of ordered states. And this is, for me, is very complicated to look at that, because it uses so fantastic new mathematical functions I haven't learned at university.
Yeah, sure.
But with these functions, with these new mathematical ideas, you can attack such problems. It's a geometrical and mathematical problem, a purely mathematical problem. And I wonder that Fisher could show that it is impossible. It's like the Fermi
it's a bit surprising,
Fermat.
Fisher always replied to these exact solutions and spotted the errors. So that's amazing.
Any more questions?
Yeah.
Okay, we thanks again Erich and Volk.
Okay, thank you.